So let's talk about thermodynamics. So thermodynamics is the science of energy. And just to kind of break that down, you see here the name thermodynamics. It's split from thermi or thermo, which is heat, and then dynamics is power or change. So the change in heat or the power in heat, things like that. And then energy is the ability to cause these changes, right? So kind of like a cause and effect situation. And then the conservation of energy principle, which is during an interaction, energy can change from one form to another, but the total amount of energy remains the same. Okay, so you can change, it's kind of like sharing, but the total amount stays the same. So you see over here on the right, it has an example where you've got potential energy, which is denoted by PE. Anytime you see PE, it's going to be potential energy. Okay, and then you have KE, which is kinetic energy. Anytime you see KE, it's going to be kinetic energy. So first, you've got a rock on a ledge or a book that you're holding in your hand, and you've got 10 units of PE. The amount in the units, not really important. Just note we have 10 right here of potential energy sitting in your hand in a book or a rock on a ledge. Okay, you have nothing in kinetic energy. Okay, nothing's moving. It's just sitting there. It's all potential. It has the potential of moving, right? The potential of using that energy. And then it drops, or you drop that book. And then as it's dropping, it's converting. It's changing from one form to another. And so you see that as it's going down, it has less and less potential energy because now it's using it. Okay, so it drops a little bit, and you've got 7 units of potential energy. So about midway down from dropping that book, maybe you've got, 5. And then the conversion goes into kinetic energy. So that 3 that you're missing out of PE has now gone into kinetic energy. And as it drops lower and lower and lower, that potential energy will go further and further down because it will be using the kinetic energy. But the total amount is still 10. You never had more than 10 units of energy, whether it be potential or kinetic. Okay, so for the first law of thermodynamics, which is going to lay the basis and the foundation of thermodynamics as a whole, is energy cannot be created nor destroyed. It only changes form. Okay, that's the first law. We can't create any energy, and we can't destroy any energy, but it can change forms. So what we just did before, where we talked through the change from potential to kinetic energy, those changes, that's what the first law of thermodynamics. And of course, it's going to get more convoluted and more difficult, as we delve deeper into it, into calculating and things like that. But overall, we're just talking about the changing in forms of energy. Okay? So, and it's really important to remember that energy cannot be created or destroyed. You may think, oh, well, I see this power plant. It's creating energy. It's not creating energy. It's converting energy from one type of energy, maybe potential, to another. Okay? So, the first law asserts that energy is a thermodynamic property. Okay, so we're going to talk a lot about properties. The first law talks about and asserts that energy is a thermodynamic property. Okay, and then of course the first law, an expression of the conservation of energy principle. Okay, and then we're going to move into the second law. The second law builds upon the first law. Okay, so they happen simultaneously, but they definitely build upon when we're talking about calculating things like this. So the first law that we talked about asserted that energy was a property. Now the second law, we're talking about, it asserts that energy has quality as well as quantity. So the first law establishes that energy is a property. The second law talks about its quality and its quantity now that it's a property. Okay? And actual processes occur in a direction of decreasing quality or energy. So scholars and experts in the community say that the best thing about the second law, the most impactful contribution from the second law of thermodynamics, is called the direction of time. right? So you can think of if an apple is rotting, okay, and you've got all of these changes, all of these chemical and microscopic changes within this apple, right? And all of these things are happening. They are happening in the direction of time that results in this apple rotting, okay? It's always going to happen in that direction. It's never going to happen in the direction of a rotting apple becoming unrotten, right? That would be backwards. So the second law of thermodynamics says, hey, we've got all of these changes in energy. Which way are these changes going? And that's the direction of a process or the direction of time. Classic thermodynamics is a macroscopic approach to the study of thermodynamics, and it does not require a knowledge of the behavior or individual particles. Okay, it provides a direct and easy way to the solution of engineering problems, and it is used in this text. Okay, so that's classic thermodynamics. And then when you get into statistical thermodynamics, that's a microscopic. Okay, it's based on the average behavior of large groups or large particles. Both of them are very important. And one thing to know here is that we're looking at thermodynamics from an engineering standpoint. I am a mechanical engineer, so I look at them from the lens of a mechanical engineer. But if you were a chemist, you would be looking at thermodynamics from a chemical standpoint. Okay, so there's different disciplines within thermodynamics because thermodynamics is a natural law. What does that mean? What is a natural law? So a natural law is something that occurs naturally in the environment. It's nothing that we have to manipulate. I don't have to manipulate an apple to rot. It's going to do it on its own. I only have to observe it. And to prove a natural law exists isn't to actually prove it by observation. It's to prove that there are no observations that disprove it. Okay? Have you ever seen an apple sit on the ground and never rot? Okay, maybe if it was frozen, but that in its sense is a lack of changes, brought about by the freezing temperatures, the slowing or ceasing of those changes, right? But if you have 100 apples, a million apples, a trillion apples, infinite apples on an infinite plane in regular, everyday environments, they're all going to rot. And so you won't be able to find one that doesn't rot. And so therefore, it is a natural law, okay? Conservation of energy principle for the human body, because we have heat, we have energy, we change the energy that we consume from food into energy that we use for work. So we are a part of this thermodynamic and energy relationship that we have. So you see the direction, right? So you have energy in, which is 5 units. Okay, got energy in, got energy storage, 1 unit, and then you've got energy out, 4 units. This depiction is okay. I want you to think maybe of like eating an ice cream, or better yet, if you've ever seen a 3-year-old eat ice cream, it's very apparent. Okay, so say they're eating that ice cream and that ice cream has 5 units and they're going to ingest that ice cream in lightning speed. And then that 5 units of energy is going to be converted within their body systems, right, into energy. Some of it they're going to store away for growing, things like that. And so maybe they'll have that 1 unit in there. And then that energy out, well, those 4 units is how you get a wild toddler that's running around. They are getting that energy out, right? They are doing cartwheels. They are acting crazy. They are running as fast as they can, jumping over all of the furniture. That is the conservation of energy. That's the energy coming in. Some of it's being stored for the processes that their body needs. And then that energy, it can't sit there. It's got to come out. And so that's how they get that energy out or anything like that. That's the flow of it, and that's the direction of it. Okay? And so when we talk about thermodynamics and energy, again, we can talk about the flow and the direction of it. Heat flows in the direction of the decreasing temperature. Okay? I want you to think naturally, things do not cool down. I know that you may think, oh my gosh, well, if we're in winter, things cool down. Don't think of it that way. Think of if you put this like hot cup of coffee, what's going to happen? It is going to cool down. Okay? If you put a glass of ice water on your countertop, it is going to the heat is going to move in the direction of the decreasing temperature. It goes from hot to cold. Okay? And so then it will warm up, right? That's because we are always trying to reach equilibrium. Is equilibrium a boiling cup of water? Absolutely not. Is equilibrium an ice cube? Absolutely not. Maybe if you're in Antarctica, that's an equilibrium there. But even there on a macro scale, we have, ice polar caps melting. The whole universe is reaching towards a equilibrium state, trying to get to where everything's kind of even everything's settled down. It's hard to see it when the time, it takes so long for things to happen. But if you want to really think about it, just think of having a cup, what happens. And it's important to remember heat flows in the direction of decreasing temperature, never the other way around. A great example of this is to artificially cool things like using a refrigerator. We have to actually manually make something to do that. We have to plug it in. We have to use energy. And that's in the state of a refrigerator, right? So that's what it takes to actually create something that goes from cold to hot, okay? So, and we will actually talk about refrigeration systems later on in this course. Here's applicable areas. You see a refrigerator right there. Of course, boats, power plants, aircraft. Applicable areas of thermodynamics is life. Because it's a natural law, you're going to find it everywhere. And where we find it everywhere, we're going to look for ways to manipulate it, like with a refrigerator or like with an air conditioner, right? We have a whole system meant to cool the home or to remove the heat from the house is actually what we do, okay? And then we've got human body. We talked about that. That kid right there eating an ice cream, going wild. Cars, these windmills, converting energy, not making energy, converting energy, right? Because we don't create energy, we just convert it. So one thing that I really want to harp on is the importance of dimensions and units. I have taught this class many times, and I can tell you this is an area that really wreaks havoc on students. And it's because we are going to be using different units, the SI and the EE, which is metric SI, and then English engineering EE units. And so we're going to go back and forth between those. You're going to have to get very good at going in between the dimensions and units and having homogeneous units to build upon. These will wreak havoc on your problems. The calculations that you will be doing are extremely lengthy. It's going to take a lot of work. This will give you a wrong answer after pages of calculation just because you didn't change inches to a meter, or something like that. So make sure that you are, and we'll do some work on this just to make sure that we're all on the same page, that you are paying attention to your dimensions and units and that you're using homogeneous units. Here are some tables. I will also give one, but we've got length, mass, time, temperature, Kelvin. We're going to be using Rankine, Fahrenheit, things like that. You've got multipliers, so 10 to the 24th. You've got a tera, giga, mega, kilo, things like that. And then you've got decis over there with pico, nano, micro. Because even though we're on a macro scale, we're going to be using, milli and centi and things like that. Okay. And so here we've got some SI units. We've got some very, very common ones. And you've even got some formulas over here. Force equals mass times acceleration. You've got things for newtons. All of these you are going to become very familiar with, and you're going to need work equals the force times distance. Huge one. So we're going to be working through all of those. We're going to be talking about area. All of these things we're really going to look into and work heavily, and it's going to be an underlying part. And the first thing that you should look at when you look at a problem are, am I using the same homogeneous units? And you will hear me say that so many times. And what I mean by that is you see you have some SI and EE units. That's because some of the information that you're going to get may be in SI, but some of the information that you have may be in EE. And so you'll have to convert it because you can't start calculating in both units. You need homogeneous units. You're going to need either SI or EE. And I will ask for that. And so now we're talking about, relative magnitudes. You've got newtons, kilogram force, pound force. And just to remember that everything that we're going to do here, we're going to assume that we are on Earth because gravity is a force, right? We're working with force, so we're going to definitely use the gravitational constant. And so a body weighing 150 pound force on Earth will only weigh 25 pound force on the moon. So don't turn in something and say, well, I calculated it as if we were on the moon, because we are not, right? And so we're going to be assuming that everything is on there, and therefore we will have a gravitational constant that is for Earth. I believe it's 9.81, but it's on the sheet. And again, just a typical match yields about 1 BTU or kilojoule of energy if completely burned. And we'll start talking about all of these. And the weight of a unit mass at sea level, that's also important, right? Because when you start talking about elevations, some of those things change. Okay? And then you see the homogeneity, the homogeneous units. Harp on that all the time. All non-primary units, which are secondary units, can be formed by combinations of the primary units. That will make much more sense when we start working about converting. Okay, so you see 1 Newton is equal to 1 kilogram mass over second squared, and then you've got one for pound force math, feet over second squared. Okay, and then you've got newtons. You can do ratios, things like that. We are going to work a lot of those. Okay. And every term in an equation must have the same units. That is our homogeneous. So even the book knows it's going to give each one of you a problem. For sure. You will not escape it. But I do hope that with all of the practice that you escape it when it comes to the assignments that are getting graded, right? Because you don't want to put in all of the work just to get something wrong, just because of a conversion at the end of the day. You guys have all had algebra. You can convert. Okay. And then a quirk in the metric system of units. I actually live and have lived in a metric system, and there's a lot of quirks. Okay, but here's just some more information. And then we're talking about, now we're getting into thermodynamics, kind of the meat of the foundational portion. So we're going to talk about a system, and it's a quantity of matter or a region in a space chosen for the study. When we're talking about the system, I want you to think about that's what we're studying. Okay? So say you have a backyard, and it's 10 foot by 10 foot. And I say, well, I just want to look at that 1 square foot over there in the top right corner, right? Okay, that is my system. That's what I am going to study. That is what I am concerned about. Am I concerned about anything else? No, I am concerned about that. That is my system. Everything else is my surroundings. Maybe the fence on 2 sides, maybe the rest of the ground on the other side. Those are the surroundings. That's the mass or the region outside my system. And then what is my boundary? Well, it can be real or imaginary. In my case, it would be imaginary. I would imaginarily draw a line around my 1 square foot of grass. And I would say, well, here's my boundary. This is going to separate my system from my surrounding. But if you're looking at a piston, which is a great example we will use, well, then the cylinder is my actual boundary, right? It's a physical boundary because I'm concerned about what happens inside the piston. Okay, that's my system. And then surrounding, which is, air, the rest of the under the hood, everything under the hood, right? Everything within the engine block. That's all my surroundings. Okay, the boundary of a system can be fixed or movable. Okay, you think about a piston. What about the rod that goes up and down? That's movable. That means that maybe my boundary is movable. Systems can be either considered closed or open, or, not included here, but very important, isolated. Okay? So if you have an open system, that means everything can get to it. Let's think about my grass example. Okay, so I have 1 square foot of grass in a yard in the corner, and, all around it is grass. It's just my surroundings. I'm just not concerned about that part of the grass, right? I'm just concerned about my system of grass. But that's definitely an open system, right? You could just walk right in it. Bugs can just fly right in it. That's fine. Air exchange, everything. That's definitely an open system. What if I closed it? What if I put a box over it? What if I dug up that square foot of grass and put it in a box and sealed the box? Well, then it's closed. It is closed. Can a bug get in there? No. Can I get in it? I mean, maybe if I broke it, sure. But can I get in it? No. But what if the earth entered into winter? Would it be affected by the temperature change? Well, yeah, because it's not isolated. So there is a third one in here, and it's called isolated. An isolated system means that it's not just closed off. It cannot be affected at all by its surroundings. Not at all. And I do want you to know that this is an assumption. Whenever we make it, that's an assumption, because there is nothing on earth that can truly be isolated. The best example that we have in everyday life is a Yeti cooler, right? It keeps ice for like 2 weeks. Does it keep it forever? No, because it's not truly isolated. But when we say something is isolated, we're going to assume that nothing in the surroundings could affect it. We are going to assume that that ice is going to be in there infinitely. It will never be affected by it. Okay? So you have open, that everything interacts with it. All the surroundings interact with it. Can come and go as it pleases. And then the closed system, well, most of the surroundings cannot cross the boundary, primarily from a mass standpoint, right? But chemicals or gas or vapors, things like that, those can. Air, gravity, things like that. But no mass can get in there. Things can't get in there. And then an isolated system means nothing can affect the system from the surroundings. No gas, no air, no gravity, nothing. Nothing can affect that system. Okay? And then we've got a control surface, which is the boundaries of the control volume. It can be real or imaginary, and we'll kind of get into that as well. Okay? So here's a good example, a good schematic of it. And so you've got the system. You see right there, it kind of looks like a little pond over there on the left. And then you've got a boundary, which you see the dotted line. That's our imaginary boundary. And then you've got the surroundings. And then over here, you see in the middle, figure 119. This is a classic example of a piston. This is usually what the piston looks like. It may have a little rod at the front. But you see that we actually have a physical boundary. You see that we have the red boundary line. But you see that you have a physical boundary line too. It's that gray and the copper. Okay, so no mass can get in through there, but energy can. How can energy get in there? Well, look at that flame down there at the bottom of 120. If I heat up that physical boundary enough, I will absolutely affect that constant, right? So for a closed system, we'll go back to 119. You've got mass is constant. And then when we start talking about putting in things with a moving boundary, you see the piston on the top is raising and lowering. Well, then that's when our mass starts moving, right? Okay, and then we've got systems and control volume. Okay, so now you've got nozzles. Okay, so you've got a real boundary, which is the black, and you've got an imaginary boundary, and then you have a direction of flow. Okay, and then over here you've got the piston. You see the little rod at the top that I was talking to you about. We've got an inlet, right, coming in from the blue. And you've got a fixed boundary, and you've got a moving boundary. Okay, and a control volume with fixed and moving boundaries as well as real imaginary boundaries. A control volume can involve fixed, moving, real, and imaginary boundaries, right? So just all of them. And then here's a good example. An open system, a control volume with one inlet and one exit. Why? Because it can get in there. Mass can get in there. It doesn't have to be completely open to be an open system. An open system just means that the surroundings need to be able to affect the system when you're talking about mass and then things like heat or gravity or things like that, right? Everything can affect it. So if you've got a hole in the side, an inlet valve, then it's an open system. And then we talk about properties of a system, because remember the first law establishes energy as a property. These are very important. A property is any characteristic of a system. Okay? And the first law says energy is one of those. Okay? Some familiar properties are pressure, temperature, volume, mass. You can take the temperature, the characteristic or the property of you as you being a system, 98.6 degrees on average. Properties are considered to be either intensive or extensive. You're going to need to know both of these, okay? For an intensive property, those are independent of the mass of the system. Doesn't matter what the mass of the system is, doesn't matter how big or little or anything, doesn't matter. The intensive property is going to stay the same, such as temperature, pressure, and density, okay? If you go and scoop up a bucket in the middle of the ocean and take the temperature, that temperature is going to be the same as if you put the thermometer in the entire ocean. Doesn't matter how big, doesn't matter how dense, doesn't matter pressure, doesn't matter the mass of the system. Density, pressure, temperature, they're all going to stay the same. The density of water in a drop of water is the same as a bathtub full of water, right? It's going to stay the same. Okay? Extensive properties, on the other hand, are those values that are dependent on size or extent of the system. Okay? So you've got volume, right? That matters. So if you have two glasses of water and one's bigger, one has more volume, it's definitely dependent on the size of a system. And then you have, talking about specific properties, extensive properties per unit mass. That's the only difference. Okay? So you've got extensive properties. And then if you talk about it on a per unit mass level, which is going to make a lot more sense when we start calculating it, then you start getting into specific properties. Okay? And so you see you've got some extensive properties and intensive properties down here on the right. And if you see this kind of like little cursive P looking there at the bottom, that's going to be rho. We're going to talk about that. So a continuum is matter is made up of atoms that are widely spaced in the gas phase, right? This property of the system. Yet it's very convenient to disregard the atomic nature of a substance that is viewed as continuous, homogeneous matter, blah, 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 is a continuum. A continuum idealization allows us to treat properties as point functions and to assume that properties vary continually in a space with no jump discontinuities. What this means is and it'll make a lot more sense, we have a lot of tables that we're going to use because we're going to have a lot of data for what's called our working fluids. So when I'm talking about a working fluid, it doesn't actually need to be a fluid. It can be air, if you have an air compressor, the working fluid in that air compressor is air. Okay? If you have a working fluid of a hose, it's going to be water. If you have a working fluid in a car, well, there's a lot of them, but let's just say it's fuel. So you have a ton of them. Helium, refrigeration for air conditioners, tons of them. And so what it talks about is it talks about, hey, we know that we have, atomic nature and that those have their own behavior and that they're not all the exact same. But overall, we can use that data to drive our tables, to drive our calculations. Okay? And you see there at the bottom, which I'm sure you guys will love, in this text, we will limit our consideration to substances that can be modeled as a continuum. That's because if we don't make assumptions, we will never find answers, right? If you're starting to talk about the behavior of refrigeration in an air conditioner, well, how are you going to ever get to the actual working of the refrigerator or of the air conditioner if you don't first assume that the refrigeration is behaving a certain way, right? And you do that based on data and on taking averages and stuff. But if you were to go on to a microscopic level and say, well, I need to find exactly how each one of these little molecules is going to act, and I need to be able to, you just can't, you can't look at it that way. You would never get anywhere. However, that is maybe a chemist thermodynamic, right? Is to get those numbers, to get us those table numbers so that we can calculate these things. So they are looking at it from here and saying, okay, well, what numbers can we put in here that will actually bring forth usable data so that when, these engineers calculate something that it will actually make sense, right? So then we're talking about density and specific gravity. So density, you see rho, that's that P over there, and it's mass over volume, and then you've got it in kilograms over meters cubed. And then you've got specific volume, which is just the per unit mass, right? So you've got volume equals volume over mass equals 1 over rho. So specific volume is the inverse of density. So you've got density, you flip it over, you've got specific volume, okay? Density is the per mass unit volume. Specific volume is the volume per unit mass, okay? So just the opposite. Okay, and then we've got specific gravity. So it's the ratio of the density of a substance to the density of some standard substance at a specified temperature, usually water. So you've got rho, and then you've got rho with a subscript H2O to identify. And then you've got specific weight, okay? And then you've got some gravities. So you've got gravities of water, blood, seawater. Of course, we're assuming all of this is on Earth, right? So we've talked about equilibrium in the states. And so equilibrium is a state of balance. That is what the world, without our interference, is trying to get to. Okay, so in an equilibrium, and not just the world, I mean like the universe. In an equilibrium state, there are no unbalanced potentials or driving forces within a system. So nothing is driving a change. When we talk about thermal equilibrium, if the temperature is the same throughout the entire system, okay? And mechanical equilibrium is that there's no change in pressure at any point of the system at any time. Phase equilibrium is the system involves two phases, and when the mass of each phase reaches an equilibrium level, it stays there, okay? And then chemical equilibrium is the chemical composition of a system does not change with time, and there's no chemical reactions to occur, so that's kind of how we measure that. So here is when we're talking about states. States are, I want you to think of like snapshots of a system. So when you're looking at a system and you want to look at the performance, well, you want to know how it behaves over time. Okay, so if you have a piston, because that's what's drawn over here on the left in A and B for state 1 and state 2. So under figure 126, if you have a piston and it's going up and down, and you want to know, well, what is happening in my system? Well, you can look at it at its bottommost or most compressed point, and you can take a snapshot. You see in that snapshot, you've got mass 2 kilograms. You've got temperature at state 1, 20 degrees Celsius. You've got volume at 1.5 meters cubed. That's that snapshot, and we call it state 1. Well, then that piston goes right back up, and at its uppermost point, you take another snapshot, like with a camera. And then for state 2, you've got 2 kilograms mass, same mass, constant, right? Temperature, 20 degrees Celsius, constant. Volume, well, now that's changed, right? Of course, it's bigger. So it's 2.5 meters cubed. And so then it'll go up and down and up and down and up and down, and you can have infinite states if you wanted to, right? Because you could always look at it, in maybe 1 minute increments or 1 second or 1 millisecond, or, we are held back with what we are able to physically measure. But theoretically, you could have infinite states. What we are concerned about is what happens in between state 1 and 2. That's what we're measuring. So we're measuring state 1 versus state 2. So if I tell you, hey, what's happening with the volume in this piston? And you say, oh my gosh, when the piston raises up, we get 1 entire meter cubed more volume. Everything else stays the same. Well, I wasn't able to just look at the system and know that. I had to take 2 snapshots and compare them together to find out what happened in the middle, in between state 1 and state 2, right? And so you've got a before and an after, see? And if you were to calculate these up, you'd see that they're all the same. But you've got just some transferring of energy by way of thermal equilibrium. So you see that we had 20, 23, 30, 35, 40, 42. We did some trading. 20 came up, 40 came down, 42 came down, 35 came down, 30 came up, 23 came up. And it all reached equilibrium, right? And so then when we're talking about the state postulate, the number of properties required to fix the state of a system is given by the state postulate. The state of a simple compressible system is completely specified by 2 independent intensive properties. You need, and it'll make a lot more sense when we start using the table, you cannot calculate anything unless you have 2 independent intensive properties. You have to have them. Otherwise, we can't. Think of it like an XY axis, but it's actually XYZ. You need 2 to get the third. Okay? And then a simple compressible system, if a system involves no electrical, magnetical, gravitational, motion, and surface tension effects. Okay? So that's what we mean by simple compressible system. Okay? And then you see over here, we've got 2 independent intensive properties, temperature and volume. And then we are going to talk about processes and cycles. So we've got processes is any change that a system undergoes from one equilibrium state to another. It's just the process. It's just the change, right? So when we were talking about, hey, what happened to that volume? Oh, we got 1 more unit. That's the process. That's what happened during that process. And you can graph it, right? You can graph that. And then you have a process path. And then the path is a series of states through which a system passes during a process. And we'll be able to graph and see the process paths of an entire system. Okay? To describe a process completely, one should specify the initial and final states, as well as the path it follows, and the interactions with its surrounding. So you've got a property A, property B, state 1, state 2, and a process path. And this will make much more sense when you start graphing. So we're talking about quasi-static or quasi-equilibrium process, and it's when a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium state at all times. So I want you to think about how this kind of looks on a graph. Okay. And so, or you know what? Let's use like a rubber band as an example. So when you pull the rubber band apart, there's a ton of potential energy loaded up on there. And if you let it go, you'll have a couple of, like big movements, but by and large, it will just sit there in just like a second. It's not going to move anymore. But there is a lot happening within that rubber band. There's it's like vibration where it'll go a little bit up and a little bit down, a little bit stretched, a little bit compressed, little tensile, little compression, little tensile, little compression, until it gets to the full equilibrium at rest. But those are infinitely small. You can't see them. And it's always very close to a state of equilibrium. And so if you were to take the average, you would actually be able to see where it's going to end up, where that rubber band is going to end up after all of those infinitely small tension pulls and compressions, right? Because it's all going right up and down. And I'll show you on a graph. It'll make a lot more sense. Okay. And then when we start talking about just more systems, and you have it over here, when you see a PV diagram, we're going to be using a lot in PV. You've got pressure on the y-axis and volume on the x-axis. And you see V1 is actually over here on the right. It has the most volume, and then we've got some compression going on the system that brings us to V2. And you see the pressure is increased, right? Because we're compressing it. So the pressure is going to increase. And you see that process path take us right from that initial state 1 all the way up to final state 2, where we have less volume, much more pressure. And so when we're talking about process diagrams plotted by employing thermodynamic properties as coordinates are very useful in visualizing the process, like I just walked you through. But some common properties that are used as coordinates are T, PV. You will hear me say PVT diagram all the time. That's because there's actually a z-axis. This is just a 2D rendition. So if we have that z-axis shooting out of your screen, that would be T. So you would have PVT on the X, Y, Z axes. And so then you've got the prefix ISO. So anytime you hear ISO, is often used to designate a process for which a particular property remains constant. So when you see ISO, think isolated, think constant, think it's never going to change. Isothermal process, the temperature is never changing. Isobaric process, the pressure is never changing. Isochoric or isometric process, the specific volume is never changing. And then a cycle is the process during which the initial and final states are identical. So you have completed a cycle. Think of a day when you're looking at a clock. You know, if your day starts, like everyone's does, at 12 a.m., your final state is identical and ending at 12 a.m. That is one cycle. You have cycled through one day, right? Or if you do it just on a 12-hour thing, if you start at 4 on the clock and you go a 12-hour cycle, it will end at 4 o'clock on the cycle, okay? And we will be working through a lot of cycles. Okay, I think I'm going to end it here just because it's going to get a little bit long, and we'll pick up with the next slide.